We're going to do a little introduction to matrices. It goes into computer programming and animation. And tomorrow you're going to have just a little quiz. It's strictly extra credit, all or nothing on each problem, 5 points apiece. Over, did you pay attention today? Or did you pay attention to the video? So it's an introduction to matrices. This was actually in Chapter 4. This was in Chapter 4 that we skipped. A matrix is a rectangular arrangement of numbers in rows and columns. The dimensions of a matrix are written as row times column. And this x should be like a little x. So if I have a matrix, an example of a matrix, I would say that its dimensions would be 3 by 2. Notice how it's a little x, kind of like a little time symbol. But you always go rows by columns, 3 by 2. Typically we use matrices for data points or points of a figure we want put into the computer, and we can translate it, flip it, shrink it, or enlarge it. Something that, if you can remember the old Nintendo where you have those mushroom Goombas of the Mario people, and they're all two-dimensional. Well, to slide that figure over, they use matrices, an addition of matrices to slide them over, or multiplication by a scalar number to flip it. We're going to go with adding and subtracting first, and you can only add and subtract matrices with the same dimension. So the dimensions we just saw was a 3 by 2, and we would only be able to add something that has a 3 by 2, 3 rows by 2 columns. And we're going to just add each element to its corresponding element in the other matrix. Numbers in the same position of the matrices are what we're going to add together or what we're going to subtract together. So you don't have to write this down. I'm going to send out a video out to everybody, but perform the indicated operation if possible. Let's talk about dimensions here. Rows by columns. So rows are what goes straight across. So like we have one row, we have 2 rows in this one, and then columns go up and down. Columns up and down. So we have a 2 by 2, and then, well, this has 3 rows by 2 columns, a 3 by 2. Well, if we have different dimensions, or to add or subtract, they must have the same dimensions. And if we have dimensions 2 by 2 and a 3 by 2, you can't add them. It's not possible. It won't translate your figure. Next example, if I can just recognize, you may want to write this down. Write these matrices down. These I'll be able to do it because we have the same dimensions. First off, each sort of box-looking thing, or each matrix, looks the same amount of numbers, same amount of elements. So again, to add or subtract, they have to have the same dimensions. Rows go left and right, and you count the number of rows, count the number of columns. In the first one, we've got 3 rows, 2 columns, and so also in the next one. So here's what I mean by adding or subtracting corresponding elements. This 5 is in the top left position. It's going to be subtracted with the top left position in the next matrix. Top right position will be subtracting the top right position. Whoops, let me back that up. My bad. The next thing you're going to see is, do we need to put plus and then negative? If it's helpful, we could. Or we could just make sense that 5 minus 4 is going to give me a 1 in that top left position. So let me get through all this work. But the top left position should be a 1. And then the top right position, it was 0 minus negative 6, giving you a positive 6. In the middle left position, negative 2 minus 2 should give us a negative 4. And I'm going to pop up the rest of the answers just so you can see them accordingly. Notice how the answer has 3 rows and 2 columns. This is what your extra credit quiz tomorrow is going to look like. We're going to go through the process of graphing a figure like you would if you had it on a computer or if you were doing some basic animation. We're going to graph these points and connect them in that order. And then we're going to see what a translate or how to do a translation using matrix addition. So let's go through and we're going to put these points onto this graph. I know I said to connect them in order, but I want it to be a closed figure. Make it a triangle. When we translate using a matrix, we're going to take our matrix of all of our points and add them to what I want to do with them. So to put each of these points into this matrix, I'm going to take each pair and put them in their own row. So 0, 4 is in its own row. 2, 4 is in its own row. 2, 0 is in its own row. So adding across, top left plus top left position. I create a new set of points. I want us to go through and graph each of these points, possibly in a different color, just so you could see it, and do it on the same axes. We can see that the original figure slid down too, just by adding these matrices. So we actually see something from geometry that we learned with reflections, translations, rotations, that you can actually do with matrices on a computer. Notice the translation matrix. For every x coordinate, I said don't move at all. I only wanted you to move the y coordinates down too, so it kind of makes sense that our figure went down too everywhere. We're also going to look at what happens whenever you have a scalar number with that figure. So we're going to use the same triangle, but we're going to put it on a new set of axes. Going to put it on a new set of axes. When I talk about enlarging by a scalar too, scalar is always some type of scaling number. Like you have in maps, 1 inch is about 50 miles. There's some type of multiplying factor. Well, whenever you see the word scalar, I'm saying take that figure and double it. I want it to get bigger. And we're actually going to see how it gets bigger. So we're going to double every single one of these elements. Doubling every single one of those elements, and they create new points. Each new point is in its own row. So we have a new point 0.8, a new point 4.8, a new point 4.0. And it does. It looks humongous compared to the first one. If I don't like the position that is in, then I could use a translation matrix on top of that to make it move down or over, so that like sometimes we're like, oh, I thought that thing was going to be inside the bigger thing. Well, if you want that, then a translation matrix goes on top of that. So let's say I want to do them both at the same time. I'm going to give you a specific order. I'm going to have you translate first and then double. So we'll go through this process, but we're going to translate first and then double. So I graph it. I'm going to put my points under the matrix and then add accordingly. I get my new points developed, but I don't want this onto that graph. I want you to also enlarge using a scalar of 2. So we're going to double every single one of these points. So this last matrix is what I'm going to graph in my new color. So let's see what happened in the new figure. First off, it should have been translated 4 to the right, because this affects your x-coordinates. Nothing up or down. So it moves 4 to the right, and it should be twice as big. That's what we did to that figure. The extra credit quiz will be looking like the past few slides.